In this video, I will be discussing the phenomenon of birefringence.
So what is birefringence? Here I have a protractor, and here I have two polarizers. When I put this protractor between the two polarizers, I get a variety of different colors. Now this is an example of the phenomenon of birefringence.
Circular polarization. We all know that a polarized light vibrates in a single plane. In fact, two orthogonal electric components make up this polarized light vibration. These electric field components move in a sinusoidal motion, and when they are in phase, they construct a light vibrating in one plane. Now let's move one of these components by a factor of a quarter wavelength. You notice that the antinodes of one wave line up with the nodes of the other. When you sum up these components, this time you notice that the polarization is rotating around the equilibrium. Birefringence. Birefringence, by definition, is when a light refracts twice in a material. An example of a birefringent material is calcium carbonate. When we take a closer look at the crystal structure of this material, we notice that it is actually not uniform and it looks more like a distorted square or a diamond. When a light wave moves across the shorter gap, as shown in orange, it will interact with more particles and slows down. It will be slower in comparison to the blue line, which travels across the longer gap. The effects of birefringence. So what happens when we shine a light orthogonal to the birefringent material? Obviously, since the incident angle is zero, there will be no refraction and the light will travel through, or so it seems. When the light travels through the material, due to the crystal structure, some of the waves will be slower than others. Now let's further complicate the setup by adding two orthogonal polarizers on either side of the material. Because the light is polarized and is traveling through a birefringent material, it will undergo circular polarization. This shift is dependent on the thickness of the material. When the thickness changes, the material is tuned to a different wavelength or color. This wavelength is blocked out by the second polarizer, while a different wavelength is seen. Other wavelengths have been slowed down at different rates, so the wavelength that is seen is the one that passes the most light through the second polarizer.
So how might this apply? Well, when changes in color are seen, it means that the thickness is changing, and also its stress. Simple experiments can be conducted with polarizers to see these effects. Examples of such materials are used in everyday objects, such as rulers and protractors. Now, another way you can test for stress is to apply calcium carbonate stickers onto objects. What this does is that you can see how much the stress or the fringe changes over time, or when a force is directly applied. And where might you find polarizers? Well, they're most commonly found in 3D glasses such as these, or sunglasses.